Hello, everybody. Thanks for that kind introduction, and thank you for the invitation. As advertised, I think we're running a little bit late, so I will get right into it. We'll talk about, I think, AI in, I think, more in surgery and in healthcare, and how we should be thinking about its use. Just some disclosures. I have two other talks, I think, in 2 days. But I should say I'm a CMO of Acrea Medical Robotics. What we're going to be talking about is big data and how really big data is visual data, and really we're going to focus on the importance of radiomics. We're also going to talk about the Ergos project, artificial intelligence, radiomics, genomics, oncopathomics, and surgeomics. Talk about some legal hurdles we have with sharing information. We'll also discuss is whole genomic sequencing affordable or not. And lastly, I want to focus a little bit on pathomics, and we'll talk a little bit about what all these things mean. So this is the journal, Artificial Intelligence Surgery. Looks like we started it back in 2021. We had our first official impact factor this summer. It's 3.6. We're very proud of that. You can see some of the editorial board members there. It's an open access journal, and it's published every 3 months, and I highly encourage you to read it if you're interested in this topic. So, artificial intelligence surgery. Excuse me, I have a frog in my throat, apparently. Thank you. So, artificial surgery really encompasses algorithms. Algorithms are simply formulas, math, statistics. You can either have algorithms that are programmed. You program it what you want it to tell you. Supervised learning, you can have unsupervised learning. Well, the algorithm can give you answers to questions you don't necessarily ask. Sounds like that's a time to make a joke about my wife, but I'll resist. And then reinforcement learning, which is trial and error, okay? And that's how we learn as humans. Now, the way those algorithms are connected is deep learning. And deep learning is a form of machine learning. It's really the architecture, how the machine learning algorithms are put together. You can have artificial neural networks, convolutional ones, and recurrent neural networks. It's based on the anatomy of the nervous system and the interconnections of neurons, okay? Because of deep learning architectures, you can answer much more complex questions. And because of that, you can develop things like computer vision, which is how the computer analyzes visual data. But because of that, you can also have things like robotics and automation, okay? Where are we? Yes. So these are some examples of machine learning algorithms. You can have logistic regression, decision trees, random forest, support vector machines. And how they're connected is deep learning, all right? You have your input layer, you have your output layer, and when you have at least a layer of 2 in the middle, that's considered a deep learning architecture. Some people think you need to have 3 layers. MIT says 2, so that's good enough for me, okay? So you can see, you can put something in, and you can have it answer very complex questions. Sometimes, you know, the information will even go backwards and then go forwards again. So another important thing to realize is that artificial intelligence in surgery has really exploded really over the last few years. Back in 2013, what we wanted to do and what we could do kind of depressed us a little bit. But at the same time, from about 2015, 2018, the computer scientists perfected things like machine learning and deep learning, computer vision, and natural language processing. And as you can see from this newer slide, it's really become exponential, the amount of people interested in artificial intelligence in surgery. So what is radiomics? You know, radiomics comes from the Greek suffix omics, or the whole, all of radiology. So radiomics technically is done by the radiologist by hand, okay? They do the segmentation, they do the calculation of the voxel or the pixel or what have you, and the gold standard is still the radiologist doing it. When you have automation, when you have computers that are able to analyze and segment the different parts of the image, that is known as deep radiomics, which is a different concept, okay? So the process of radiomics really follows a structured pipeline. You have your medical image acquired, you do your segmentation, we'll talk about that in a minute, a lot of people don't understand that. You have your feature extraction, you have your databases, and then you can mix it with clinical and genomic data and what have you. And And then you can identify meaningful features using deep learning that can give you insights that the human brain can't necessarily understand, but that the deep learning algorithm does. And it can give you guidance on things like tumors that have good biology, tumors that have bad biology, simply based on an analysis of features from the image. So step one, image acquisition. Usually it's from CT scans, MRIs, PET scans. This is really, it's a very labor-intensive procedure that the radiologist does. You look at the region of interest, or the ROI, either in 2 dimensions with a single image, or a 3D region, with the 3D reconstruction, okay? So this is just an example of segmentation. Segmentation is when you tell the computer, this is the pancreas, that's a segment. Then you say, this is the tumor in the pancreas, that's another segment. So that's what segmentation is. In a very simple way, okay? So it's really important to have a clinical focus, but from an AI perspective, the computer is actually able to look at all of the pixels, or all of the voxels, the 3D voxels. The 3D pixel is known as a voxel. And instead of looking at one point, like a radiologist does, usually they just put them in a machine and they say, okay, this is what the voxels are in this area. An algorithm can look at every single voxel, every single pixel in an entire CT scan. Arterial phase, venous phase, non-contrast, everything. So it's much more powerful, and the human brain cannot understand that amount of data, okay? And that's known as the black box phenomena, and that's what a lot of people are afraid of AI, quite honestly, because AI can realize things that we just can't comprehend. Next thing that's important in radiomics is feature extraction. Based on the shape, is it a rough edge, is it a smooth edge? The intensity, again with contrast, does it light up, does it not light up, or what have you? Textural features, and all sorts of things. Now, normally the radiologist does this, but as I mentioned, there are programs now that can do this autonomously or semi-autonomously. Database building is the hardest part. Collecting the data, getting everyone on board to share the data is the hardest. Now, a lot of people erroneously think that you want data from the same CT scan for the algorithm to be strong. That's not the case. You want images from as many different places, as many different quality as possible to get a robust and strong algorithm. Then, of course, you need model validation in application, okay? That's just a little background on radiomics. Now, why am I talking about radiomics? Because I want to talk about the ERGOS project. The ERGOS project is for surgeons, and what we are trying to accomplish is to collect radiology data, pathology slide information, clinical data, and ultimately genomic data to create a very powerful AI-powered tumor board. So we can guess a little bit less with our patients. We can, instead of say, oh, let's try this chemotherapy, repeat a CT scan in 3 months and say like, oops, that wasn't the right one. We don't want to look at just a few data points. We want to look at all of the data points. Okay, so how are we going to do this? We've identified about 7 hospitals so far that are part of this project in Germany, in Belgium, in Japan, in Italy, and Serbia, just to give you an idea, all right? And we have a cloud-based system where all of the data is being uploaded into the cloud and kept. So why did we think about this? Because one of our collaborators, Professor Takeaki Ishizawa from Osaka University, some of his younger colleagues looked at a single-slice CT scan arterial phase of hepatocellular carcinoma. Retrospectively, they were able to find out, looking at people that lived less than 2 years and people that lived more than 2 years, they created an algorithm to essentially create like a radiologic biopsy, like a virtual biopsy, if you will. Going forward, with about 75, 80% accuracy, they were able to predict which tumors were going to have a bad biology or a good biology. So it really changes our way of how we should be doing liver surgery and maybe pancreatic surgery. It's not only is it resectable, but should it be resectable? Okay, so they looked at a single slice arterial scan image, right, of the cancer. We thought, what if we looked at the three-dimensional images? What if we looked at all of the phases? What if we looked at the 3D reconstruction? Then we thought, why stop there? What if we looked at the pathology slides, looked at the pixels of the tumor, compared it to the normal parenchyma? Then, what about whole genomic sequencing? Whole genomic sequencing isn't as expensive as it used to be, right? These are just the groups that are involved. Okay. well, I'll keep talking about this. Whole genomic sequencing costs about $1,000. It used to cost about $60 million with the Human Genome Project back when it was initially done, but now it's about $1,000. I know a lot of patients that would pay for that to have their tumor sequenced, okay? But let's talk a little bit about the legal hurdles. It's a bit of a problem for hospitals to share data. We're working through that. That's a big part of the Ergos project, is getting documents signed and lawyers to get all on the same page and figuring out ways for everyone to get paid. One solution might be the blockchain, okay? Because then we can register everybody's data. A patient on their phone could just check, oh, my data was used for this. I approve this, I don't approve this. And then every month they might get a report, okay, I made $50 from my data this month, or I made $5,000 from my data. I don't know. There's a famous patient, Henrietta Lacks, from the United States in the 50s. She had a cancer she died of, and a lot of pharmaceutical companies made a lot of money off of her cells. So it took her family decades to kind of get some compensation for that, and we want to avoid that, obviously. So this is just a little bit of a paper of why we don't currently do whole genomic sequencing. Really, the price is right now. So once we're able to prove the concept that we're able to collect data, we're able to analyze radiology images and pathology images with clinical data, our plan is to then get funding so that we can do the whole genomic sequencing. Okay. So a little word about pathomics. Pathomics actually is probably the most powerful omic for pancreatic cancer. So what's interesting about this is it's not like every omic is equal in every different cancer. So this is just an example from Chinese. They looked at all sorts of different features from pathology slides, neurovascular invasion or what have you. And they were able to come up with an algorithm that was able to really give information on that tumor in a much more powerful way than simple pathology. So why am I so interested in this? Because how you combine different omics isn't as straightforward as we thought. So we wanted to go back and we looked at the literature. How many people have combined pathomics and genomics, or genomics and radiomics, or all three, okay? And on top of it, will the combination make the algorithm weaker or stronger? We don't really know. So this just gives you an idea of what has been done combining radiomics and pathomics. You can see really the leader in radiology, the leader in AI right now is radiology. They have access to all of these images. They're probably a decade at least ahead of us. But the next group that is really, really well poised for AI are the pathologists. Okay, so you can see the vast majority of omics, of multi-omics, if you will, is between radiomics and pathomics. You have things here like breast cancer, cervical cancer, prostate cancer, pulmonary cancer, things of that nature. Now, what about combinations of genomics and pathomics? You can see we have some studies looking at genomics and pathomics. Nobody's looking at radiomics and genomics, at least of what we found as of this review. But there are some people looking at all three. You can see in the corner on the right, people looking at genomics, pathomics, and radiomics. Two papers that are looking into this. Now, we're not just limited to these genomics, right? You have transcriptomics, proteomics, metabolomics. You have so many omics, it's like omic soup, if you will. But we want to start somewhere, and we wanted to use the model of an AI-powered tumor board. Again, because what we've noticed is we're looking at very limited data as we make decisions on our patients. We want to eliminate the guessing, and we want to give people a better idea of what immunotherapy to take, whether surgery is indicated for them, whether they should get radiation therapy or what have you. Okay, so just to wrap up, big data right now is visual data. All right, it's very important for you to start saving your data, but remember on Ergos, there's that word surgeomics. Okay, we saw some beautiful videos from the last presentation from Matthew. It's very important that you start recording those studies, because what the dream is, what the holy grail of Ergos, of AI really, is to have intraoperative decision support. We want to look at preoperative information from the biopsy. We want to look at preoperative radiology imaging. We want to look at the clinical data. And then in the operating room, we're going to start to collect information because we want to know this patient with a solitary pancreatic metastasis. Should I go ahead with the Whipple? I didn't know that they had a metastasis, but I found it intraoperatively. This patient who maybe needs an Appleby, are they a good candidate, or are they not a good candidate? This is what we want, and this is what we're hoping for. ICG can illuminate images, so augmented reality is becoming broader, where we want to mix it with fluorescent imaging. Depending on your wavelengths and the shape of your wave and the amplitude, you can actually look into the liver several centimeters just with a camera, okay? So it's a very exciting time right now to be a surgeon, I actually think. So I think whole genomic sequencing is actually affordable. Again, it's $1,000. Maybe you're gonna have to spend $1,000 to look at the tumor genome and to look at the normal liver or pancreas parenchyma, so maybe it's $2,000. But I think a lot of people would pay for it, and it'd be money well spent. In the University of Ohio, Tim Pollack's group is looking at people with cholangiocarcinoma. And what they're doing is they're analyzing their genome, and they're finding out mutations. And they're finding mutations that have immunotherapy or chemotherapy that targets, or immunotherapy, I should say, that targets that specific mutation. They're putting all of that information into an algorithm, and what they're creating now is essentially a study with an N of 1. And they're giving people chemotherapy or immunotherapy cycles tailored to them, and they're having incredible results. And this is a really exciting time because we can really finally give people what we've been talking about for over a decade, precision medicine, okay? So this is kind of what we're hoping for and what we're dreaming for. So deep pathomics may be the most powerful predictive omic in pancreatic cancer, so it's important to keep an eye on these things, not even for surgeons. I think we really need more multi-omic integration. We have to start looking at transcriptomics, proteomics, and metabolomics. This takes money. So this is why we're having a stepwise approach for Ergos, so that we can convince people to give us more research dollars. The biggest hurdles, I should say, are really legal, and they're not computational. It's surprisingly easy to do the algorithm. I think we all think that the computer science is the most difficult part. It's not the most difficult part. The most difficult part is collecting the data. We have the most difficult part, but we're perfectly poised to collect all the data. Specifically as surgeons, we have access to all of the data, okay? Universities are really perfectly poised to help with multi-center international data collection. I'm part of a European grant called Compass AI, and we've been given 5 million euros to develop guidelines for the safe integration of AI in healthcare in Europe. I'm tasked with doing the integration for surgery. So there's a lot of research money out there. I encourage you guys to read the journal. If you're also interested, there's a new organization that we created called Artificial Intelligence Organization for the Next Generation of Surgeons, AONS, which one of our goals is to put academic surgeons interested in research, interested in AI in contact with industry to help develop their ideas. Because I think for us really to break through to the next level, we really have to have an integration with industry, because a lot of this stuff is just simply too damn expensive. So with that, I will end. Thank you very much.